Thank you. Welcome, everyone. So my name is Tomasz Pęczek. If you ever want to reach me, find me. I'm on Twitter. The handle is right there in the corner. And what I'm gonna be talking to you about today is real-time capabilities in ASP.NET Core applications. You probably are well aware what real-time web applications are. You use them every day, like Twitter, Facebook, Gmail. The idea is simple. Deliver the new data as soon as possible to the client without any interaction from his side. And this kind of application has been created for a long time, long before dedicated technologies for this existed. Back in those dark ages of web, so I don't know, 10 years ago, we were using techniques like cross-frame communication or long pooling. Those were essentially hacks. They were abusing some aspect of browsers to create the impression of application being real-time. Luckily, at some point, the HTML5 milestone has reached the browsers. It was a point in time lightly related to a new version of HTML standard that brought a number of new APIs to browsers, to web developers. And among those APIs, there were two dedicated for real-time technologies. A very well-known WebSockets and a lot lesser-known servers and events. And since that time, the web is constantly evolving, constantly growing. New standards are appearing regularly and are being quite eagerly adopted by browser vendors. And one of such standards, finalized last year and already adopted by almost all the browser vendors, are push notifications for the web. And those are the technologies I want to focus on today. I'm going to start with probably the most well-known one, WebSockets. WebSockets, when they arrived, they were a long-awaited revolution. They were bringing something that was missing in the web since somebody decided that he wants to deliver something more than a static web page, a bidirectional communication. After establishing a WebSocket connection, both parties, the server and the client, they can send messages to each other at will. And those messages can be either text or binary. Those capabilities makes WebSockets the closest thing that the browser has, similar to the raw network socket. And those are very powerful capabilities. Such a low-level API allows for building almost any functionality on top of it. Of course, in software development, nothing is for free. And in case of WebSockets, the price for this API, for these powerful capabilities, is complexity. WebSockets couldn't be delivered on top of HTTP. They required a new protocol. And authors decided that this protocol will be binary. And that had consequences. The first consequence was that infrastructure was not able to handle this. WebSockets connection in its early days were often dropped. Issues with infrastructure are easily solved. You give it time, it upgrades, it gets solved. The second outcome of using new binary protocol is not that easy to solve. This introduced a new programming model for the web. And till this day, we often pay the price of developers using WebSockets incorrectly, because on low level, it's not easy to do so. It requires custom APIs. And ASP.NET Core delivers the API to use WebSockets in two parts. First part is a feature. Those of you who are a little bit more familiar with ASP.NET Core architecture probably know that features are abstractions of server capabilities. Request is a feature, response is a feature, TLS is a feature, response buffering is a feature, and WebSockets are also a feature. This feature doesn't have to be implemented by the server itself. For example, Kestrel doesn't support WebSockets out of the box. So what you usually do, you grab additional packet from Microsoft, include their middleware for WebSockets into the pipeline, and after that, you are safe to use them. What feature can do for you is two things. First of all, it can detect that incoming request is a request to establish a WebSocket connection. And it can accept this connection. In a result, you will get the second part of the API, an instance of a WebSocket class. That's a very low-level class, and it actually covers both the server and the client. It has a very rich API. From typical server perspective, what you need is a method to send data, receive data, close the WebSocket. You can also use the property to check the WebSocket state to protect yourself from sending to a not open WebSocket. And in order to add WebSocket support in your application, you need to use those APIs. What's the best way to do it? Again, if you are a little bit more familiar with ASP.NET Core architecture, you probably know that the best place to deal with protocol-level aspects in ASP.NET Core is middleware. Those are the nice pieces that the request goes through before it reaches the business logic. So in case of WebSockets, we also usually create a middleware. And this is a blueprint for such a middleware. A wall of code. Yes, don't try to read it. Don't try to memorize it. There will be links at the end to demos. You will grab all this code. Here is just a background for me to show you what is the flow to handle WebSockets correctly. So let's focus on the invoke method. The first step is to check if incoming request is a request to establish WebSockets connection. WebSockets, in order to establish the connection, are using the standard HTTP upgrade flow. So this essentially checks for connection and upgrade headers. If it is a request to establish connection, we accept that request. So ASP.NET Core will send the one-on-one response for us, will set all the technical headers, it will give us the WebSocket class. Now, WebSocket class, as I already said, is very low level. It's not something that you want to pass to the higher layers of your application. You don't want your business logic to deal with such a low-level API. So what you usually do is you wrap your WebSocket instance in something that represents a connected client. And you hand it off to some kind of either a manager or service, something that delivers connected clients to the higher layers of the application. And after that, you wait. That's the key aspect of properly handling WebSockets. You need to wait. You need to wait long enough for socket to terminate the connection. In a server scenario, you typically wait for client to terminate the connection. It's very rare for server to do so. So you cannot leave the middleware flow until the client decides to close. If you do, then the thread will be aborted, the connection will be destroyed, and you will be left with an instance of connected client that is essentially broken. When client finally decides to disconnect, the server needs to complete the close handshake. For that purpose, we actually need to send the same close status, close description as the client did. At this point, you can remove your abstraction from the service manager, leave the middleware flow. Now, at this point, we need to focus a little bit about what you are waiting on, that receiving loop, that point in which you'll be waiting for client to close connection. There is a chance that in the past, you have been writing WinAPI applications, I don't know, in C, C++, C# even. If that is true, then receiving loop will be familiar to you. In those applications, the key part was event loop. It was listening for events from operating system, sending them to other parts of application. That's how everything works. Mouse click, mouse move, etc. That's how all native Windows applications works. It's kind of similar for WebSockets. Receiving loop is a constantly spinning loop which receives from WebSocket. And then it specs the type of the incoming message. Now, if the message is a close message, then yes, we leave the loop, we pass the status description to middleware, we are done. But if it's either text or binary message, then we need to read the payload. If it's text, then we need to deal with UTF encoding, and only then we can notify the higher layers of the application about the new data. For this purpose, we can use events, callbacks, whatever suits our case best. Reading the payload, again, is not that simple. there's one more loop involved. This has two reasons. First of all, there is a buffer inside the WebSocket class, and that buffer has its limits. So if incoming message is too big for WebSocket class to handle at once, it will give it to us in parts. Also, the standard itself allows for message to be sent in multiple frames. In that case, there is no obligatory period between the frames. So it would be inefficient, at least from the WebSocket perspective, to wait for all the frames to arrive. It will give us some data as soon as possible. Maybe we can do something with that, improve our performance. What that generally means, that on that received part, you need to check the end of message flag. If that is the end of message, nice. If not, you need to, again, receive in loop until you reach the end of message. And you need to constantly either process the data or concatenate them. Only when you are done, you can return it. There's one more thing which is crucial to handle WebSockets correctly in ASP.NET Core: exceptions. The receive loop, the receiving method, can throw a WebSocket exception. And what that means in most cases is that the connection has been terminated abnormally. Simply client crashed, network got disconnected, whatever. The problem is, when this happens, the exception is the only indicator. The status of the WebSocket doesn't change. It's still open. So even if you are conditioning your sending logic with the status property, you will be writing to an invalid WebSocket, you will be getting further exceptions, and you will be wondering what is going on. So you need to grab this exception, return the control to the middleware, remove the connection from your list, leave the flow. That's it for receiving from WebSocket. So like 3 screens of code, 3 levels of nested loops, dealing with low-level binary data. We can see the complexity. It's easy to get this wrong. How about sending? Sending is relatively simpler. In most cases, those 2 lines are fine. But we can already see that API allows us to implement more performance scenarios. That first parameter is an array segment. So if we are building a big message over time, let's say in simplest case over a memory stream, right? We can get the access to the underlying array and move through that array with the array segment. As soon as new data are available, we can push those data to the wire. We can minimize the cost of pushing the whole message at once, and we can give the client a chance to process data early. So if you may need this kind of performance, there is a way to do that. So we know how to receive, we know how to send. Of course, there is more to WebSockets than just sending and receiving. There are 2 very interesting mechanisms in there. One is subprotocols. Those are logical subprotocols. On technical level, this is a very simple thing. It's just a header on that initial request. What it allows you to do is, first of all, have different subprotocols, but second of all, easy evolve your WebSocket, especially if you forget to design for evolution in the first place. That often happens. Imagine yourself in a startup scenario. You are moving fast. You are building the simplest thing that can possibly work. And you need a WebSocket endpoint. And you're building something raw, something that returns some simple text data. It is enough for now. And your application has become successful. And in the worst case scenario, that endpoint has become some kind of part of public API, either for other internal services or for something external. The bottom line is, you don't control all who use them. So you cannot simply change it. What you can do is, let's say that the new subprotocol is supposed to use JSON, so you design that subprotocol and you name it. Now the upgraded clients can advertise the support for the new subprotocol. This is simply done by passing the name of the subprotocol when you're establishing the connection from the client perspective. ASP.NET Core will give you a list of all the sub-protocols that client has advertised as a property on the context. You just pick the one you want, pass it to the accept method, establish the connection. Then you initialize an instance of client that speaks this new protocol. If an older client connects that doesn't speak the new protocol, it hasn't upgraded yet, it will simply not advertise support for any sub-protocols. So you build an instance of, of your client representation that speaks the old protocol, you pass that to the higher layers. If interfaces for those representations are the same as they should be, the higher layers of your application doesn't even know you're speaking multiple protocols. That's nice decoupling technical aspects from business aspects. The second nice mechanism in WebSockets is extensions. The standard actually allows for different specifications to change how the binary framing is behaving. I have seen two specifications of extensions. One is for technical level multiplexing of WebSocket connection, and it haven't been adapted. Generally, it's not in use. But the second one is for compression, and it has been adapted by most of the browsers. You can probably guess which one doesn't adapt it. And it is a potentially very useful mechanism. The algorithm used for compression is deflate, so it can give you nice performance improvements, especially if your messages are somehow based on text. Unfortunately, ASP.NET Core does not provide support for any of the extensions. So if you find yourself in a scenario that you think you might need compression to get your performance right, you need to reach out to community. There are community projects that attempt to deliver compression for WebSockets for ASP.NET Core. They usually replace the middleware from Microsoft, give a little bit different API. So if you find yourself in this situation, go, pick up one, exchange your implementation, measure, then make a conscious decision. There's one more area which is worth to discuss in context of WebSockets in a special way. Security. There's a lot of questions about security when it comes to WebSockets, because they are not HTTP. Most web developers are familiar with HTTP, not with WebSockets. So how to do authentication and authorization? That's the most common question. The answer is simple. Actually, the HTTP way. We authenticate, authorize that initial HTTP request before the upgrade. There are limitations. The client-side API for WebSockets does not allow, simply there's no way to provide custom headers. So what you have out of the box is either basic authentication or cookies. If you want to do something more modern, more API style, you need to use different patterns. If, for example, you would like to use tokens, there is one pattern I would personally recommend. It's generally used, fairly safe. You use a secondary endpoint. You create an endpoint to which you will make a standard AJAX request with the token. That endpoint will create a very short-living cookie. That's important. And you will authenticate your WebSocket request based on that cookie. And the cookie needs to die immediately. This way you can use tokens or other mechanisms with WebSockets. Encryption, this works exactly the same as with HTTP. WS schema, the schema for WebSockets, has its secure counterpart, WSS. It's using TLS, nothing new. What is new is a very unique for WebSockets security hole, cross-site WebSocket hijacking. It comes from the fact that WebSockets are not subject to same origin policy. So from the browser perspective, it's perfectly fine for any web application in the world to connect to your server. That's probably not fine from your perspective, right? So it's our job to make sure this doesn't happen. Luckily for us, the authors of the standard has decided it probably would be nice for implementers, for server-side applications, to at least know who is connecting. So client is required to send the origin header. and that header needs to point to the application that is attempting to make a connection. So a standard part of your WebSocket support should be checking the origin connection. The ASP.NET Core team is actually working on integrating the cross-origins resource sharing middleware with the WebSockets, so it kind of works both ways. But right now, that's up to you. You need to make sure it's done okay. And let's say for now, this is all you need to know about WebSockets to use it in your application. Let's move on to its lesser-known sibling, server send events. Server send events are lesser known mostly because when compared to WebSockets, at first look, they look quite poor. They offer unidirectional communication. After establishing the connection, only server can send events to the client, and events must be text-based. So that's a lot less than WebSockets, right? So why such a technology exists? The reason is, the way server send events has been designed gives implementers a way to make them extremely performant. A lot more performant than WebSockets, if you know what you are doing. That is because server send events are extremely simple. In order to establish a server send event connection, all client needs to do is send a GET request with an accept header with value text event stream. If server understands server send events, it will respond with OK response, content type, text event stream. Done. The connection is established. It's a long-living HTTP connection with all its consequences. Both parties know not to close it too early. From this moment, client starts listening for the events, and it does so by looking for special characters. The first special character is end of line. If line is empty, it means that the event has just ended. You can call the client-side code, whoever is listening for that event, it's ready. If the line was not empty, it means that certain field of an event has ended. And the identifier of the field from its value can also be separated by a single special character. There are 3 types of fields in server send events. Identifier of the event should be unique, optional, doesn't have to be there. Event type can be used to out of the box add business level multiplexing. It doesn't have to be there, you can skip it. If it's there, different event types gonna be triggering different events on the client-side API. And finally, the data field, 1 or more adjuncted to each other, that's the payload. So whoever of you have been ever writing either parsers or writers in low-level languages like C, C++, or even in C#, especially with the newest features like spans, etc., knows this can be implemented very efficiently. You can easily scan ahead, scan backward, use it to your advantage. The second advantage of server send events is that it inherits all HTTP capabilities. That's an HTTP connection. So authentication, authorization, well, there are limitations. The same as with WebSockets. The client-side API, the event source object, doesn't provide a way to send custom headers. Same origin policy is applied, and you can use cross-origins resource sharing to work around it if you need. Compression works out of the box. That well-known compression from your response. gzip, Bradley, they are perfect for compressing text. So there's a lot of performance in there. One important remark though. If you want to benefit from compression, you must do it in a layer you control. In order to efficiently implement server send events on the server, you must control the flash operation. You don't want your event to get stuck in the middle in the response buffer, right? That would destroy the whole point. So if you're doing a compression, you need to control it. In context of ASP.NET Core, that's okay. If you are using response compression middleware, which supports both gzip and will support broadly with next release, it checks if the current provider supports response buffering. If you have disabled response buffering, it will check if it should compress or not. For example, for gzip, that means that on .NET Framework, it will not compress. On .NET Core, it will compress. That's one of small differences. Flash on gzip stream on .NET Framework is just a no-op. In .NET Core, it does what it should. If you're not using compression in the layer you control, disable it. Remember, they are intermediaries in the network. Worst case scenario, you are running just behind a reverse proxy. For example, IIS. IIS loves to do that. IIS loves to add its own compression on top of what's coming out of ISP.NET Core. So it will kill your performance. So set the content encoding header to value of identity. That's not perfectly valid value for a response, but it's generally accepted and it gets the job done. There's one more very interesting thing that servers and events inherits from HTTP2. That's a technical level multiplexing. And it's about third time I'm mentioning multiplexing. It might be worth for me to explain what I have in mind. Imagine yourself an application, a content management system, which is completely configurable by the client. The client can put as many widgets on the page as he wants. And let's assume all those widgets are real-time widgets. In perfect design, they all handle their own connections, right? They are completely decoupled from each other. That's what we want. In real life, that's usually what we not implement. TCP/IP connections use resources. Actually, every browser has a limit of how many parallel TCP/IP connections can be opened. This limit is not always enforced for WebSockets. That's an implementation detail. But generally, it is there, and it is there for a reason, to not overwhelm the client. So to have a nice behavior, we usually implement some kind of a dispatcher, which unfortunately immediately becomes a coupling point in our design. And that dispatcher is doing business level multiplexing. For servers and events, it's better out of the box. They have that event field. So the API itself is able to do that. For WebSockets, you have to design your own protocol with routing information in there. But if you detect you are running over HTTP2 and you are using servers and events, you can go crazy and have as many parallel connections as you want. That's due how HTTP2 handles TCP/IP connections. There is only one connection to certain origin. Every request response becomes a logical stream within that connection. That's true for every servers and events connection. So the only limit at this point becomes bandwidth. Bandwidth is always a limit. In most cases, you don't get to it. HTTP removes all the other obstacles. You are left only with bandwidth. And of course, any other HTTP capability that makes sense for you, for your case, can be used. There is nothing against it. So how do we implement servers and events in ASP.NET Core? As you are probably expecting, we need a middleware. That's the right place. And it's actually quite similar to the one from WebSockets, only simpler. The first step is to check for that accept header on an incoming GET request. Is that a request to establish servers and events connection? If yes, then grab the response buffering feature, disable response buffering that's needed for performance, set that content type, flush the headers, you have the connection. Now, there is no dedicated API for servers and events. So you need to deal with the raw response object. And you certainly don't want to pass it to the higher layers. So you wrap it in some kind of representation, which is going to be writing to the response in servers and events protocol. That's the key place for achieving performance on the server. The way you write events to the response is how performant your connection is going to be. And you hand off that representation to some kind of client service, and again, you wait. This time, you wait for connection to be aborted. This is how closing the connection is represented in server send events, regardless if it's clean or not. There is no special message. Server will simply see that client has shut down the connection. When that happens, you can remove the abstraction from service, leave the middleware flow. And that's almost everything to server send events. There are like 2 configuration commands and 1 potentially useful feature, automatic reconnects. On client side, server send events support automatic reconnects out of the box. They will always attempt to reconnect. Or server side, we can help them to do it right. If we include IDs in our events, then client will observe the last seen ID. So when he loses the connection and attempts to reconnect, it will send that last seen ID. When he finally gets through to our server, we will get that value in the header. If we are storing our events in some kind of NoSQL database or something else, we can query all the later events, send them to the client will nicely update. This can be used for special business cases. This must be used if you really want to support server send events on IE or Edge. IE or Edge don't have built-in support for server send events. You need to use polyfills there, and polyfills depend on long pooling, AJAX, last seen event ID. The obvious consequences, the performance is not as good as it could be if it would be a native implementation. And at this point, it's a great moment for me to mention SignalR. If you go to the SignalR repository for ASP.NET Core, of course, you will read that it is an incredibly simple real-time web for ASP.NET Core. And that's true. And that's achieved through a very high-level abstraction on top of what I have just shown you. SignalR introduces its own protocol, hub protocol. This protocol identifiers caller and callee, and those are a role within the single interaction. And they can be like 3 different interactions. An invocation. I'm sending something to you. I'm expecting confirmation, potentially some data back. One-way invocation. I'm sending something to you. I don't care, I'm moving forward. And streamed invocations. I'm sending something to you. I'm expecting a stream of responses. And finally, you're going to tell me you're done. That's it. From business perspective, there is nothing more in SignalR. So that's an RPC protocol, which actually allows you to do a lot on top of it. The second abstraction that SignalR provides is transport. And SignalR simply states, transport is bidirectional, binary safe, text safe. That's it. Under the hood, that means that most of the type WebSockets will be used. If that's not possible, server send events and post. If that's not possible, long pooling and post. And there is some level of control over that. And from very high level, that's all about SignalR there is. Back in ASP.NET days, SignalR was like a go-to option for all your real-time needs. In ASP.NET Core, it's probably gonna be similar, especially that we right now have Azure SignalR services, which solve additional issues in form of scaling and availability. So why did I just spend like half an hour talking to you about WebSockets and server send events? Because sometimes it's better to start with the low-level technologies. The first group of such cases is when hub protocol doesn't match your business needs. Either you are not okay with RPC style for some reason, or your business case requires one of the specific features that those low-level technologies provide, which is not exposed through SignalR. The second case is special technical performance requirements. If you require different way of handling the transport that SignalR allows you, then it is better to start with the low-level technology. The general rule is you don't want to fight with the framework. You don't want to find yourself in the last 10% issue. That's extremely expensive. So think in advance. And that's it for what HTML5 has brought to us and what high-level abstraction we have on top of it. Let's take a look at the latest, greatest, the web push. You certainly know what push notifications are. You have cell phones, Twitter app, Facebook app. You're going out of the shower, that's where all the great thoughts are born, and you decided to share your thought with the world. And you're going to sleep and you made the mistake of leaving your phone on the nightstand. You are almost sleeping and bzzz. Who doesn't like that, right? That kick at the end of the day. So those are push notifications. And now the browser can do the same for you. Nice, right? In browser, push notifications work in two ways. If you are online, the notifications is immediate. It is reaching your notification center, some kind of message pop-ups, some sound might be related, depends on your operating system, its settings. If you are offline, the notification can wait. Your application, your server-side part of the application will send a notification. It will wait somewhere. That's quite a unique ability. Up to this point, to achieve something like this in the web, we had to do a lot of infrastructure coding on our end. Now web somehow gives us to us. How? Well, the general flow of web push looks like this. Sorry, it's late, right? Okay. It looks like this. That's better. You can immediately see how this is being done. There is a third party, push service. This is how client and server exchange the notifications, while client only receives. So this architecture, quite unique for the web, requires a new programming model. That's a subscription-based programming model. And if you were listening on Adam presentation, you already know that the client-side part of push notification depends of service workers. It is the service worker which is the actual subscriber. Well, it would be strange to create subscription in context of a page or something else. So to start working with push notifications, you need to install a service worker. If you have a service worker, you can attempt to create a subscription. For this purpose, you need a set of keys on the server side, a public and private key. Public one needs to get delivered to the client side, preferably in a safe way, and pass to the subscribe method. Now, if the attempt to perform subscription succeeds, the communication with push service was okay, you are receiving the subscription object, which contains a bunch of very important information. First of all, a URL, a unique capability URL to which you are sending your notification, and a set of further security keys, security values. Now, this object needs to be securely delivered to server. If you leak those information, anybody who gains access to them will be able to send notification to the subscription. You don't want that. But if you have the subscription, you have safely delivered it to server, all that is left on the client side is to actually receive the subscription, show it to the client. We do that in the service worker by listing for the push event. This is it for the client side. And in the process of establishing that subscription, I have already mentioned security values, keys, a number of times. Security theme is strong with this technology, and it should be expected. You saw the diagram. There is man in the middle by design. So security and privacy must also be by design. Let's deal with the security first. The push service must know we are entitled to send notification to certain subscription. This is achieved through standard HTTP authentication, so the authorized header. That's the most typical method if we are talking about post request, and post request is a way we actually send a notification. Under that unique capability URL, we make a post request with our notification. And we need to set the authorized header according to one of two schemas, web push or Vapid. Actually, the web push is already deprecated. That's not that bad because there is very small difference between them. The only difference is that web push is actually using two headers. In authorized header, it's sending the token. In Vapid header, crypto key header, it's sending your public key. Vapid does the same in authorized header, simply using two parameters. The important part is the token. It's a JSON web token in JSON web signature form, so 3 blocks, base 64 encoded, comma separated. Header, copy pasted. It's always the same. There is only one signature algorithm. The structure of body is important. It's built from 3 parameters. Audience, that's the origin of push service, expiration time, and subject, that's some kind of information about us, our URL or mail to. And why it is important to take a look at the structure of the body? Because it tells us that tokens can be easily cached per audience of the push service, per origin. And there are not so many push services out there. Every browser vendor has like 1 to couple. And there is a value in caching. That third part, the signature, is calculated using very strong cryptographic algorithm. And very well-known feature of strong cryptographic algorithms is that they are expensive in terms of CPU and memory. That's actually the goal, so you cannot easily brute force them. They must be expensive. So cache your tokens. And if you have the token, you can start building your request to the push service. Set either the authorized header or authorized header and crypto key header, and add the payload. And in case of payload, we are expecting that it should be encrypted. And in this case, web push is using yet another specification, encrypted content encoding. And that's a very low-level specification, designed to provide a way to store data on a server in a way that server cannot understand it. It deals with IES in GCM mode, padding, etc. You don't want to deal with that by yourself. Grab some kind of library which supports that. What you need to know is how to use it in context of web push. And there's gonna be a lot of cryptography details here. If you remember correctly, when client creates the subscription, it sends us some security values. Among those values, there is a public key for the client generated especially for this particular subscription, and an authentication secret, a random secure value. When we want to send a message to this subscription, we need to generate a public key pair on the server side for every message, every subscription. That's expensive. The public key from that pair became something called key identifier in encrypted content encoding. The private key, together with public key of the client, goes through elliptic curve, Diffie-Hellman algorithm, whatever. Something called agreement is generated. And that agreement is hashed with authentication secret. This is how the key is generated. That key is used to encrypt the payload, sent to the push service. Push service, whoa, that's complicated. I don't know how to guess all those values. He cannot do anything with that. Sends that to client. Client grabs our public key from the key identifier, grabs his private key. Again, elliptic curve, Diffie-Hellman magic. The same agreement is generated. Client is the author of the authentication secret. He can hash. Finally, he has the key. He can decrypt the data. This is how much encryption details you need to send push notifications. That CPU memory expensive. It's worth to keep that in mind. On top of that, on top of security and privacy, there's one more thing in web push, attributes. All of them are delivered through HTTP headers. There is one required one, time to leave. It tells the push service how long the notification is supposed to wait. So if you send a value of 0, it must be immediated. That's actually what Slack is doing with its notification. If you have Slack open, you will have notifications. They don't appear if you close your browsers later. Additional attributes, urgency, it allows to condition the delivery of notification with the state of the device. That's important for mobile devices, where power is everything. So we can say, this notification, it has to be delivered no matter what. This one, okay, you can wait for high battery state or good connectivity like Wi-Fi. And last attribute, topic. That's the unique identifier of notification. You can use it if you want to replace previously sent notification. If client hasn't received that one yet, it will only see the new version. Now you know. Now you know how all three of modern real-time technologies work, how, if you really want to, you can implement them yourself. And you might have a lot of questions. Probably the most important one is, which one to choose? And obviously, I can give you only one answer. And you know what that is? It depends. So when you're about to choose, first of all, consider your primary use case. If you're about high-performance streaming from server to client, servers and events might get that for you. If you're about durable notification without guarantee of delivery, web push might help you. For all the generic use cases, WebSockets are your hammer from the toolbox. They will nail almost every requirement. And SignalR is a very fancy hammer, a lot more user-friendly. And there are always trade-offs. If majority of your users is IER Edge, you don't want to go for servers and events, you don't have performance benefits. If minority is ER Edge, you might either use the polyfill or implement a fallback from servers and events to WebSockets. That is actually an often used pattern. In case of web push, there is that security dialogue that you probably know because early adopters of web push didn't care about being user-friendly. You go to the page, bam, accept notifications, right? Go away, no. People don't like that. Don't do that. Don't be like that. Build a nice flow that encourages user to subscribe. If they decide to click a subscribe button, they will accept. Slack does it fairly nice. And for WebSockets, it's easy to get them wrong, to make a mistake. So, make the right choice, consider your trade-offs, and remember about the future. If your application becomes successful, you don't want that to be an issue. You will need to scale. It's 2018. We know how to scale. We scale out, right? We want multiple instances. That solves all our problems. For WebSockets and servers and events, that means load balancing. The only potential issue, if you have endpoints with your web application, which is typical, you have multiple instances. One instance is a trigger. It's hard to send a broadcast. You need some kind of message broker behind. Redis does it nicely out of the box with a PubSub protocol. Everybody are subscribers, one publishes broadcast. For web push, it doesn't require the web context. If you have the subscription, you're simply making a post request. So whatever you want, microservices, picoservices, functions, it works. Just make sure you have sharded your subscriptions equally. You are using all the instances. Web push is expensive, CPU, memory. But if you remember about that, your application will be successful. And the last helpful piece I got for you is a bunch of links. My blog is in there. I write about this, I write about other stuff. Couple useful demos, some hopefully useful libraries you can use in your projects, get them right, make your users happy. If you have questions, I'm on the break, I'm after the conference, you can grab me. I respond to emails, I'm on Twitter. Thank you.